Um, Random access.
Yeah, are you sharing? I'm not able to see the screen.
Oh, sorry. Yeah, so ROM read only RAM random access memory, right?
Yeah.
Okay, so so how so ROM is definitely read only. So how it will look like, right? So definitely there'll be certain some memories are there, right? Some memory will be there, and then the predefined value will be stored here, right? In the ROM. It's a fixed value will be there in the ROM, right? Fixed value, fixed value basically. Cannot change it on the fly, or even we cannot it's a manufacture, like the ROM is programmed while manufacturing only. So it's like a there's like different types of ROMs are the EROM, electrically programmable, EPROM basically electrically programmable ROM, EPROM, and I don't really recall what other types, but definitely it's electrically programmable. So it's while manufacturing only it is programmed the fixed values, and that will be read. Okay, so how it's basically so reading means how we can read. So there'll be some fixed size will be there, right? So there's
Yeah.
like word size. So we say data size or word size basically. It can be 1 byte, 2 byte, whatever it can be somewhere and then there'll be some location. How many locations are there? So at least this is called depth, okay, or address, and basically address depth. Okay.
Okay.
So, how we represent any memory? We represent by the uh, basically rectangle size. So let's say we call it a 32-bit cross. Let's say this may be any size 128 locations. Okay, so this is how we represent the memory size. Okay, this you can say mem size. Okay, so any memories, it can be 2 bit, 1 bit, whatever. This is the size of memory. How this how we represent it. So to access this memory, so what ports will be there, right? So the ports will be, this is like, let's say ROM is there. Okay. So what we need address. Okay. Then some clock because sequential, and then definitely we need if you reset is not needed because already initialized, and then we need basically depth. Sorry, address. Hmm? Because we are which address we want to read, and then it's always read, right? So whatever whenever we change the address, or we can have a read enable also, the ROM enable basically. It will basically enable. Okay, so when we enable and we provide address, it will read. Okay, and there'll be a data out. Data out. Okay,
So we
what will
cannot
the
write in that. It's only.
it's a ROM, it's a read only, so you cannot write it. So it's just enable is there. And what will the size of data? Size of data is like this size, which is 32-bit. Whatever size of memory is there, the word size is the data size. Okay, and then what will the address size? Address size will be log base 2 of 128, whatever the depth this. Okay, this will be the address size, log base 2. So how for the 128-bit, how many 7-bit address? 7-bit address. So this is how we define the size of data and size of address based on the memory size. Okay, and let's talk about RAM. Okay, so RAM is also, there are many type of RAMs are there. Okay, one is like a single port. First of all, we understand what is RAM. Okay, so RAM is random access memory where we can it's there's no data at beginning, or it can be any random value at the beginning. Okay, in each location, and size is again memory size we represent by this only, like the this data size, DW we can say, and then the depth. So let's say this is also 32 bit. Let's say this is the size of the memory. Okay, but here we can write also. So there's two way of writing. Like we either it will be a dual port RAM or dual port. Dual port means like we'll be having a data like data in separate. Two ports will be basically data write address. I can cleanly write. Okay. What will in dual port? What will be there? Like data in. Okay. Then write address. Then there will be a write enable. Okay. And then address. So address is already in, right? And then here it will be what? From the two port means parallel ports are there. Okay. Which can be accessed together. So here will be what? The read address. And there will be a read enable. But the data out will be here, right? Output. And here data in is input. Data output. And definitely there will be a one clock also. Okay. And and there'll be this is called dual port RAM. Okay. Or we can say it's a dual port RAM. And one is called single port RAM. What is called, or you can say it's a not two port RAM basically. You can say. And what is single port RAM? Single port RAM is also similar size, but there will be only one port for access. So either we can do a read or either or write we can perform. So there'll be a clock, there'll be a data enable, data in, data in, and there'll be address. It's not a write address or read address, it's an address. It can be either for read or write. And there'll be a enable, and there'll be a write or read. Okay, so write underscore read. Okay, so it's the same signal will define whether it's a read or write. Okay, so when it's a one, it is write. When it's a zero, it is read. Okay, and there'll be definitely a data out. Okay? So these types of memory is there. Okay, and there is also a memories are there where we'll be having only like one data port. So one data port, because the data buses are usually very wide buses, right? So if we have many like data in and data out, separate buses are there. It means like it will be taking a lot of space on the chip. So to realize that or to minimize that, there is only one data bus, which will be a read or write. Okay, so this data. So in that case, we say it, basically we call it a tri-state bus. Remember I said right initially tri-state logic. Okay, so this bus is tri-state. Okay, tri-state bus.
So
So
we
they
get in out
yeah.
that.
So basically how it's like basically uh, So this bus is like a bidirectional bus. See, we can write like this. Okay. So whenever there is a, it knows like internally the memory knows whether it's a write or read. Okay. So whenever we make it write, right? So write means like the internal logic. Whenever the write is there, so basically tri-state buffer is like this. Okay. This is tri-state buffer. So there's a enable is there. Enable, and then this is tri-state buffer. You can say. So and this is D in and D out. Okay. So whenever enable is there, it will pass on the data D into D out directly. Okay. And whenever enable is zero, this buffer will drive Z here. Z means tri-state voltage. Basically, when zero is there, Z like um, this is like 0 voltage, right? And zero is called like ground. Okay. And then one is called VCC voltage. Okay, some voltage basically. And the tri-state is like in between voltage, which is like in point 0.5 or basically VCC minus ground by 2. It's a voltage, that voltage. So the logic will drive the this voltage, uh, middle voltage, so that the outside value can drive anything. So whether it's zero, if it drives zero, it will pull down the whatever this will be driven, it will appear on the bus. Similarly, when the read is there, so outside logic will drive Z, IZ. So there'll be like two. Whoever wants to drive the data, other should know like it's driving it. So that other can pull down its logic. Pull down means like it will put into high impedance state.
Okay,
Okay.
so this is you are talking about the bidirectional data bus, right?
Yeah, bidirectional bus. Yeah, so bidirectional data bus. So single port can be with the two different data bus, also data in and data out, and the single port RAM can be with the bidirectional data bus also. Okay. So we'll design like a ROM, then we'll design a RAM, single port RAM, and dual port RAM, and the single port RAM with the bidirectional data bus. Okay, this is 4 types of RAMs we'll try to design. Okay,
Hmm.
so let's start the code. We create a project. We call it memory. Let's design a dual port RAM first. Okay. Let's say DP RAM. Okay, dual port. What are the ports? Like definitely clock port will be there, reset will be there, and other than that, data in, write address, write enable, then read address, read enable, and data out. Okay. So this is like you are learning FPGA programming, right? So what happens like whenever you write a code, okay? So ultimately it will implement the compiler will understand the tool code, and it will understand like where to implement the memory on the FPGA. So what happens like memory, sometimes memory is implemented with the logic on the FPGA, okay? And I'll give you just a brief of FPGA, right? What FPGA contains, okay? That I did not give. Yeah. Basically, FPGA like this, very big, okay? And there'll be some IOs are there. IO. So IO is different kind of IOs are there. So it's like a, we call it SERDES, basically serializer, deserializer. Okay. And then some IPs will be there. There's some processor is also there now. But small. I'll not talk about the processor and all. I'll talk about like then some interface will be there which can program it. It's called NPI. And also like there'll be a lot of programmable logic. Okay, it's called PL. We say PL. Okay, programmable logic. So what PL basically it will contain, or we also say it fabric, which is programmable. So what it contains, like there'll be a CLB inside the uh, each. There are a lot of CLBs will be there. CLB, it's called CLB, configuration configurable logic block. Okay, well, logic block. Okay, and these CLBs are basically, it contains LUTs, LUTs, LUT. It contains flops. Okay, flop. Okay, and like this, like some gates. LUTs is only contain LUTs and flops. Okay, and also there'll be like, so a lot of LUTs will be there and flops will be there. And also it contains the DSP block. DSP is like a digital signal processing block. So digital processing signal block means the DSP will be kind of multiplier. So a lot of multipliers will be there on the FPGA. Okay, and also it contains the block RAM. It's called block RAM. There'll be like block RAMs. Okay. Hmm. So based on our code, like VHDL code, how we write it for the RAM. Okay, VHDL RAM code. Okay. So based on our coding style, the tool identifies whether to use your RAM, RAM, whether your code should implement this RAM, which is already there on the FPGA, these RAMs, or it can implement that RAM in this logic also, because RAM is ultimately a storage element, right? So it can pick up so many flops are there, right? And create a RAM. Okay.
Okay.
A lot of flops are there. So it can create based on a coding style. can create a RAM using the logic, or it can create using the these RAMs directly. You can, so these RAMs are 18 kilobyte size. Okay, so it is very big RAM. So so it can implement either using these RAMs, or it can implement these RAMs. Okay, based on flaws. So what will happen if you're let's say you're coding a very small RAM. Okay, let's say size is just a 16 bit. Okay, and then by 64 depth. Okay, so it's very small RAM. Okay, so for these small RAMs, it is good to code. Let's say at some point of time you'll be writing the code and you'll be putting on the FPGA, right? So FPGA is also having limited hardware. You cannot utilize like 100% hardware or more than that, right? You have to fit your logic inside the FPGA only. So at that time, when the small RAMs are there, it is good to use smaller RAMs in the logic and bigger RAMs in the uh, memory. So this way, it will you should know what is the coding style I should write so that it will implement this and this.
Okay. And in the LUT, what we have that LUT?
LUT is a lookup table. So basically, what will happen from the logic, whatever VHDL code you write. So basically, your code is what? Your code is let's say you're writing an AND gate. So AND gate is truth table is there, right?
Yeah.
AND gate truth table will be like 0, 0, 0, 1, 1, 0, 1, 1. Okay, and then output is there. So this logic, so definitely AND gate is not there on the FPGAs. FPGAs having lookup table, so it will program these lookup table uh, and behave like a AND gate. So it's like it will program this truth table in some LUT, and it will act as a AND gate.
Okay.
Understand? So these LUT basically. So why you can say like why is not using AND gate? So this way like it's very flexible to program it basically.
Mm.
Or some any logic is there, adder logic is there. So adder how it can implement in the LUTs, right? It can implement program LUT such as that it will behave like a adder FPGA.
Okay, so they are these LUT also interconnected with each other.
Yeah. So it will program like such that this LUT will talk to this LUT and this LUT will talk to this. So it's like highly sophisticated hardware which will be programmed based on your logic.
Mm.
That's why FPGA is like a reprogrammable device. But the ASIC is like the whatever hardware is created, it will implement, it will pick up the gate and then it will fabricate,
Mm.
and it will be a permanent hardware for your logic.
Mm. Okay.
So let's create DP RAM. So DP RAM is what? Is so we have a clock, first of all, clock, reset. I will show you how it's based on the coding style, what it will implement. Okay,
Mm. Okay.
reset and then data in.
And can you please make this window bigger?
Okay. Let's say choose memory size. I just comment memory size so that we will know what we write. Memory size 32 bit plus 128. This size we are going. Looking at. So logic will be there. What data is 32 bit, right? So 31 down to 0. Okay, and then write address.
That is a vector, I think.
Vector. Sorry. Yeah. Then write address in. So write address will be what? 7 bit, right? Because it's 128 depth. 7 bit is like 6 down to 0. And similarly, write enable. Then we have copy this. Read address and then read enable. Okay. Then we have a data out, which will be output, right? So out. Okay. These are ports. And then we create a memory, right? So where we'll write? We'll create a memory. Okay. Memory is what? Two-dimensional, right? This is two-dimensional memory. Okay. This signals are single dimension, right? Right? It's a single dimension expanding, but this is two-dimensional. So width is also there and then height is also there.
Mm.
So we cannot directly write a signal which is two-dimensional. So we have to make our own type which be two-dimensional. Okay. So for that we declare a type. So this is how we declare the two-dimensional memory. So we have to declare our own type, which is mem. I guess I shown you, right, or not, or maybe type mem is array 0 to 127, right? Is
Yeah.
array of data size, which is like a vector of a vector 21 down to 0. This is a data size, right?
Okay, okay, it is like row and columns, this entirely.
Yeah, row and column. So and now this is a type we declare. Now we declare a signal, which is a memory. Okay, signal we can say dp mem, whole put mem. Any name you can put, can give. So which is like a name mem. Okay. Now we write. So we have to now write it. Okay. So there will two process will be there, right? Write and read. Okay. So we do process. Definitely it's a sequential, right? So this become a memory, right? So you remember flop, so, or register or memory. So if a memory element is there, we have to definitely use a clock to write and read. Okay. So clock, reset. Read we can do, but writing must be there clock and process. Okay. Again, reset. Basically, okay. As of now, we'll do and we initialize memory. Okay. It's a two-dimensional memory. You remember I was doing all zeros, right?
Yeah.
When the two-dimensional is there, others, then one more others, others of others.
Mm,
Zero. It's a two-dimensional initialization. Okay. Else if clock equal to one and clock when and then we write it, right? So if when we write, when the write enable is there, then only we write, right? Other take one, then memory. So memory we have to access by the address. So whatever first access will be giving when you access this array, right? So when you give a address, it will take the this array this address. Okay. And whenever so it will give a element of size. It will access the element of this each element. Okay. So memory we give a address. So address is what? A right address. Okay. So in VHDL, the right address is actually the standard logic vector, right? So we have to so this we cannot access this element. We have to type is different. So whenever accessing the element, we must provide an integer value. But this is not a type integer, right address. We have to convert to integer. Convert underscore integer. Okay, we converting to integer. So now we are accessing that element or that memory. So whatever address is, so it's an integer access, and then assign it to, we give a date at that address, we write this data in. Okay, whenever write enable is there, we write to a location which is by depicted by write address, and write the data into that location. Okay, and then end if. This error is there. Why error is there? Because you're using a library which is not declared here. So we can use underscore unsigned.org. Or dpmem, sorry. Signal is dpmem. Okay. So you see, it will give error. I just commented. You see, it will give error for that, right? Because this library does not have this function. Now it says no error. Okay. And then end if. Okay. So the write is done. Okay. Now let's do read. Okay. Then the clock read is like whenever we read, we get output of data out, right? We say data out, and then when the read enable is there, basically data out gets the same way. We want to access a location of data. A data out is single dimension, right? It's not a two dimension. Let's say we want to access a location of, right, the same memory, right, and as a read data. So we did read, and it should be a read address. So read address. Now memory is done, right? So let's save it. Let's create a test bench for it so that we can access it and see source. Okay, so we add, let's say, let's take this car. We make component output. And we declare the same as a signal also. Now we declare, we do port map. And do position association because same names are there. Now we drive the puts. So we create a clock already created. So clock gets clock after not of clock basically after I do a reset. Reset is active high create rate. So we initialize it the reset so that it can take the initial value here. Zero initial value one. And we make it zero after some time. Now we drive the value. Okay. Process. Okay. So first value, let's say we have to wait because reset is a wait for 100 ns. 110 we can make. Okay. And then we drive data in. Okay.
This weight we can put outside also, right? That weight for.
No. This wait for is only in the process. Okay. It must be in the process. It's a sequential wait. It has to be in process. Data in assigns to some value. So 32 is right. So we can give A5A. X we can write like this. And similarly binary we can write like this. No X. A value is 1010 0 10 and 5. And then we can repeat it. But same thing. So this is how I can write the binary value and this how hex value. X we write it become hex value. Okay. Then address. Okay. So write address. Address is 7 bit, 8 bit, 7 bit. So X. So let's write on the 10 location. Okay. X 10 means like A only, right? 0A. And write enable. Write stick 1. Okay. And then we can initialize this also 0. Then this is right, and then we write one more right. Okay. Now wait for 10 nanoseconds and write another value which is E5, let's say. Okay, and then we pull down right and then do a read. A address, not A address, let's write on the B address. Okay. And perform a read. So read means like data in won't be there. Anyway, it will hold the last value because we are not changing data. And then we read address. Let's read from the A, okay? And read enable. Okay. And then we make that okay. And write enable we should make 0. Okay. So we don't want to write. It's a dual port, right? Read, but it can write also. Okay. There's not, but we can write also. At the same time, we can write also. Okay. Let's do the dual port. Okay? Let's not let's write and read together. Same data we were writing at C address. Okay, not making this. No. Myra इधर जाओ. Wait for 10 ns. Make both 0. Okay. Let's simulate it. Okay, just error. You can see here log and so sim behave. Damn it, login. Expression has element expected is 768. Okay. This one is saying like so we are writing hex, right? So it is taking as a 8 value. Okay, so let's write in binary. Or let's change it quickly to not 128, maybe 256 location. Okay. 7 means like a 256, right?
Yeah.
Oh, okay. 68. Yeah. And this is not, this is data is 31 bit, right? Not here also. Data was 31 bit, down to 0. And this will become 256, 255 basically. Okay. That's fine. Either way, you have to write binary value, right? Hex we cannot write. So also we add the we can let's add the signals of this duty also inside. Okay. So what is the object? So of duty, it's not showing the mem object. DP mem. So this we can see the memory also. I can add to waveform. Okay. and then we restart. At this time reset, at reset we are initializing the memory, right?
Yeah.
So you see that this is the memory. It will look, there is a memory, okay? So you can see the memory is created a two-dimensional array, and which is of 255, 256 depths, right? Until 255. So this is the memory created in the simulation. Okay, and then now we are writing A on A at A address. A is 10 address, okay? And write enable is 1, okay? Let's see. At 10 address A is written. At 11 address B5 is written. At 12 address B5 is again written. See? We're writing B5 at B address, and at C address we are writing B5. So we are not changing the address and data in, but we pull down the enable. So you see that there's no write happening any on any other location.
Mm.
It because we basically even though we change the address also, it will not write.
Mm.
Okay. You see, now we are doing the read also, right? We are reading, and what address we are reading? We are reading the A address. A address what we have written? A5, right? So you see, after read enable is there, and then once it's sample on the clock edge, this is reading the value A5, right? We write to the 10 address A, and then we read address 10, we get the data out as A5. Okay, you understand this?
Yeah, I understand.
So now let's do a synthesis. Okay, basically what we are getting from it. We do synthesis. So this will create a distributed RAM. Distributed RAM means I said right. This is called block RAM, which is created in the fabric. Okay,
Mm.
basically the block RAM, which and this distributed RAM is created in the logic.
Okay, and the LUT.
LUTs, yeah. So it since this coding style, whatever I have written, it will create a distributed RAM. So I will show you. It will show the synthesis result. It will show you what it's created.
Mm.
The synthesis is running. Synthesis will give you give you the like what logic it is taking to create from on the FPGA.
Okay, and the elaborated design, it says the circuit diagram, right? Elaborated.
Yeah. I'll open that also. It will just give you a block. It will memory block, and then it will have some ports and you see it has created so many two-dimensional array created, right? So DP memory is showing like how many flops are there. Okay, because we are using the flops, right? So it is created the flops.
Mm.
Okay, and uh, and I'll show you the synthesis result. Synthesis result we can see here summary, project summary. You see, post synthesis results are utilization is like it is using LUTs, flip flops, IOs. Okay,
Mm.
I said right, it will take some LUTs, some flip flops to create a distributed RAM because it's a distributed RAM.
Mm. Okay.
Okay. Here in detail utilization is shown here.
So we also need to check this synthesis report.
Yeah, you can check it. It's not showing. We did not run the report. It's showing like it is taking uh, slice 8,000 slice, and so basically each slice LUT is basically it's taking 8,000. I said right, it will take some logic, and then it is taking this many registers, and then some muxes and all, and then bonds. So this is basically distributed RAM. Okay, and now I will create the like I will tell you why it's created a DP RAM. Why it's
And
created a distributed RAM.
okay, in devices it showed some diagram something.
Okay, that
Device.
device. So
Yeah.
it shows a device basically. So how the FPGA, this FPGA, whatever you selected is like this. And it's telling like where the logic is put. So the logic is put inside these areas, the X1, Y1, and looks like this IO bank, and on the device, like where the logic is there. So this, not sure. Yeah. It's not visible. It basically,
Maybe
zoom it, it looks like
yeah, it shows the
it's some logic is implemented.
yeah, it shows
Yeah.
the gates, some buffer or gate, I think some gates.
This is a LUT, right? I said a LUT is a function, so it creates 5 input function
Hmm.
LUT. Uses a LUT to create some function, basically.
Hmm.
Okay. So now let's understand the design. So if you initialize the memory, so basically in general, any memory hard block, which is actually a memory, cannot be initialized by the user. Okay. By on the reset. Okay. It will have its own reset value, and so you must not initialize the memory. So this, let's say, we can say it's a distributed RAM, and we can copy paste, comment it, and then paste it. Okay. Now we're writing the block RAM. Okay. So block RAM means we must not initialize it. We have to comment this. Okay. We are not initializing it. Still again remove it. Okay. No comment. Yes. So we have removed the reset thing, right? So we remove this also. Okay. And also the read data should be without clock. Okay. So we should read the data here. Okay. So this will create a block RAM. Okay. And there will not be any read enable. You just give an address and it will read the data out. This
So
synthesis is.
Okay, in real devices, it is also automatically I mean, enabled.
Yeah,
Reading.
enabled. Yeah.
So we created this 32-bit multiplied by 256, right?
Yeah, yeah.
Okay.
So we reload the.
So that will give the total memory, right? If I multiply it.
Yeah, yeah. So now you see, it's become a RTL RAM because I have removed the initialization, right?
Hmm.
And there is no basically the read and reset is not used. And if you double click, it's nothing is there. It's because it's using a memory itself. Okay.
Hmm.
And
Okay.
if you see the report, synthesis report basically in the project summary, it's using a LUT RAM.
Hmm.
Oh, still, oh, sorry. It's still, there's three types of RAMs. Are there basically? Just got confused. So this is a not distributed. This is a flop RAM, register RAM, basically register based. Okay, it is a register. Okay,
Hmm.
and one more is like is there like this is called distributed.
Okay.
Distributed RAM does not use the flops. Okay, you see, it uses LUTs only. You see, LUT RAM and the LUT. It's using LUT and LUT RAM. So, okay,
Hmm.
and but not using the flop registers. Not at all registers. Okay, you see in the report if I report the utilization summary. You see, there's no slide LUT register. Earlier, you see the registers was there in the previous report, but now there's no register. One more thing, understand. So LUT, when we create a when you create a flop based RAM or register based RAM, it takes a lot of slices. And now we are creating the LUT based RAM. It is again it's become smaller. Okay.
Yes.
And now we create a block RAM. So how block RAM will be there? So this is distributed, and we can copy paste it. We can copy this. Copy this.
Can we continue tomorrow, Sunday?
Just 5 minutes. Okay.
Okay. Okay.
So again, reset will not be there. This is block RAM. The block RAM again, the read enable will be there, but there will not be nothing will be initialized. Neither memory, neither data out. So reset will not be used. But this will create a block RAM, I guess.
Okay.
This is it.
Yeah, based on the memory type, we are just modifying our
The code. Yeah. Based on the code, basically you can say generate the memory, or we can say for a given type of memory, there's a certain coding style is there. In future, you want to optimize the usage of FPGA, right? When you become FPGA engineer, so you want to optimize the usage of FPGA. How you want to utilize the FPGA? You must know this where to put your logic in the RAM or the distributed RAM or where. When I say block RAM, BRAM is used.
Hmm.
Now no LUTs, only BRAM. Okay, and we see the utilization summary here. See, only block RAM is used. See, no LUTs is used.
Hmm.
And if you just say, it will be again RTL RAM only. It will be because a RAM type only, a specific RAMs. You see, now it's just a memory, right? So there's no IOs also. Just a RAM is saying, oh, IOs are there. Sorry. So it's the same way, like it's RTL RAM. First one was like logic because we initialized everything, so it created whole logic. It's not a specified RAM, right? And the second, next two are kind of RAM, which is like implemented in the FPGA, LUT RAM and then block RAM. Okay, then yeah, we may continue tomorrow. Okay.
Yeah, okay, yeah. Okay. Okay.
Okay. Bye.
Yeah, bye. See you.